Alright, welcome back guys for one last section. This is section 9.7, and we're going to be applying some of those exponential functions to solve problems. Okay, and we're going to be looking at processes that we can use exponential functions to model that are actually either increasing in quantity or decreasing in quantity. We're going to model those processes as either continuous growth or continuous decay. Okay. Alright, and we're also going to be utilizing that special irrational number e that we've talked about some. Okay. Alright, so let's look at this graphic right here. We use p typically because lots of times we'll be modeling populations, the growth or decline of a population. Your independent variable is going to be t. These are going to be functions of time, and time is typically going to be measured in years. And then this is the generic form of our exponential equations. We'll talk about our exponential function, and we'll talk about these parameters. Okay. Alright, so how do we know this is an exponential function? Well, because if the variable is t, where is it? It's in the exponents place. Okay, the k and the p naught, that's what you call this. Or you could say p sub 0 because the subscript here is a 0. The reason the 0 is there because this is the initial quantity whenever time is 0. Okay, but t is going to be our independent variable. And this is a function of t, or time. It's going to usually be measured in years. And then k is going to be the rate of either growth or decay. So think about when we were talking about interest or the growth of an investment. Okay, in that situation, k would be just whatever that interest rate is. And you have to express it as a decimal. And then finally, p naught here is going to be the starting population or the starting or initial amount. Okay, because we're not always going to be talking about population growth or decay, as you'll see. But anyway, this formula is basically the formula that we saw previously when we had p for principal and then 1 plus the APR over n raised to the n times t power. Okay, whenever you let n, or the number of compounding periods, increase infinitely, then it approaches this number right here. Okay, let me show you this. This is really interesting, actually. This piece right here approaches or converges to this value, or this number e, which we've talked about. Remember, e is roughly 2.71. Okay, so when we were working with those interest rate problems, interest wasn't growing continuously. It was growing, or it was being compounded monthly, maybe daily, quarterly, etc. Okay, but we can sometimes model processes as if things are growing or decaying continuously. And that's what we're going to be doing today. So that's where this e comes from. Okay, so this is really that financial formula for compound interest, just when the compounding rate is continuous. Okay. Alright, so let's try one. So you can think about this function right here as our template. For each problem, we're going to have a different initial amount. We're going to have a different rate of growth or decay. Alright, well, let's look at example 1 here, and it's a population problem. It says in 2013, population of Ghana, located on the west coast of Africa, was about 25.2 million, and the exponential growth rate was 2.19% per year. Okay, so already we can identify this is P naught. Okay, this is our initial population, and then the 2.19%, that is our K. That is our growth rate. So it says, part A, we just want to find the exponential growth function. So similar to those problems dealing with compound interest, all part A is prompting us to do is just simply write this as a function of t. Okay, so it'll equal P. Well, actually, we're going to replace. You know what? Let me write the formula or the template up here, so we can have it to refer to. P naught times e to the power of kt, k times t. All right, so I'm going to fill in for P naught and for K. So P naught is 25.2 million. Now you don't have to actually write that as 25,200,000. You can just write 25.2. You just need to be aware that this function, the outputs will be the population in millions as a function of time. And then e to the power of k, well, k, because k is 2.19%, that as a decimal will be 0.0219. Okay. And then t, and that is our function right there. Okay, so it's this function right here that we would use to model the population growth of Ghana, at least for a period of time. Okay, lots of times, guys, these models are pretty accurate over a certain number of years. Okay, there may come a time when the population of Ghana is no longer increasing exponentially. And then it could eventually start to decrease. Okay, so, and that's where, like, domain restrictions might come in. But anyway, that's part A. This is our exponential function. Part B says, estimate the population in 2018. Okay, so we're going to do that using this formula, or this function here, but we need to figure out in 2018, how many years is that from 2013? Well, 2018 minus 2013, that's 5 years. So in other words, we want to see what will the population be in 5 years. So we're just going to evaluate the function when t is 5. Okay, times 5. And you can put all this into your calculator, or let me try to use the online T84. Okay. All right, so 25.2. Now, I would use, for your E key, I would use this one down here. So say second, and then your LN key, and then K was 0.0219 times 5. I'm going to hit enter, and this is my answer in millions. So you're going to have to look and see how do we want to round. It doesn't say, but your homework will. Okay, I'm going to round to maybe the 10th place, so this would be 28.1 million. So 28.1 million. You got to keep that word million in there. All right. Now, part C says, after how long will the population be double what it was in 2013. Okay. Well, the way we solve this one is we're not trying to figure out what the population will be after so many years. We're trying to do just the opposite. We're trying to figure out how much time has to pass before the population doubles. Okay. So what we're going to do is first figure out, well, what would doubling the population be? Well, if it's 25.2 million and we double that, which means we multiply it by 2, okay, that will be 50.4 million. So in other words, for what value of t, or how many years has to pass before the population is 50.4 million? So to do this one, you actually set your function equal to 50.4 million, okay? And we're going to solve this for t. So here you're doing just the opposite. Instead of plugging a number in for t and seeing what the output is, we know what the output is. The output is the doubled population, 50.4 million, and we need to solve this equation for t to determine how long it's going to take. And this is actually a very common problem right here, guys. You'll see we have a formula for it down here, but this is an exponential equation now, and that's why we spent a lot of time solving those exponential equations in 9.6. Alright, so to solve this one, I'm going to take the ln of both sides, or the logarithm of both sides. Okay, so I'll take the natural log of the left-hand side. This will equal the natural log of the right-hand side. Just recopy all that. Remember, what the logarithm allows us to do is to get access, or to move that exponent out in front. Okay, and so if we do that, I get 0.0219 times t times the 25.2. And then, no, I'm writing that wrong. Wait a minute here. Oh, no, guys, I'm going about this the wrong way. No, the first thing I need to do, I'm sorry, got a little ahead of myself there. No, the first thing that I need to do is I need to get rid of this 25.2 in front of the e, and you'll see why here in a minute. Okay, so I'm going to divide both sides by 25.2. That's going to be my first step. So on the right hand side, these divide out, and we're going to be left with just e to the 0.0219 times t is equal to, well, this is going to go 2 times because we just doubled 25.2 and we got 50.4. So I know 25.2 goes into 50.4 twice. Okay, and this is actually, you're going to see this again here in a minute when we find a formula, or come up with a formula to find the doubling time, how long it takes a population or whatever to double. You're going to end up with a 2 right here. Now I'm going to take the natural log of both sides. So the natural log of 2 is equal to the natural log of e, and all this in the exponent's place. And like I said, this exponent will move out in front, so we'll have the natural log of 2, I need to scroll down here, is equal to 0.0219 times t times the natural log of e. Okay. Well, if you recall from 9.6, the natural log of e is 1. That's what's nice about using the natural log. And so you can just cross that out, because 1 times this other factor is just this other factor. All right. But now we need to get the t by itself, okay? So the t is being multiplied by this decimal, so I will divide both sides by that decimal. And on the right-hand side, those coefficients divide out. It's going to leave me with t is equal to this value right here. Now again, this is the actual, this is the exact value, but because these are application problems, we're probably going to want approximations for these values. So you're probably going to want to type them into your calculator and round them appropriately. Okay. I'll use this calculator. Well, okay, so the natural log of 2, make sure you close that parentheses before you divide, divided by that decimal, 0.0219. And hit enter, and this is what we get. If I round this, say, to the nearest tenth, this would go to 31.7 years. Okay, 31.7 years. And so that means that's how long it'll take the population to double if it continues to increase exponentially like this, at this same continuous exponential rate. Okay, but again, you know, in the real world, things don't, complex processes like that, the rate at which they're increasing exponentially, if they are, is usually never quite the same. But nonetheless, this can give us a good idea. Okay, so about 32 years, okay, if we rounded it to the nearest year. Now what about part D? It says, at this growth rate, when will the population be 40 million? Let me put part D over here. Well, this is the same type of problem. Instead of setting our function equal to the doubled population, we're going to set it equal to 40 million and solve it for t. Okay. So I'm going to take a function, set it equal to 40 million. Just recopy everything else. Okay. And you're going to solve it the exact same way. You're going to start out by dividing both sides by 25.2. Oops. Okay. On the right hand side, those divide out. Guys, I'm not actually going to divide this right now. If it doesn't divide evenly, I'm just going to look at it like it's one number right here. You can put it in parentheses if I want. And that'll leave me with e to the 0.219 times t. And now I'm going to take the natural log of both sides. So this will be the natural log of that quotient is equal to the natural log of e to the 0.0219t. Again, use power rule to move your power there out in front of your natural logarithm. The natural logarithm of e is 1, so we'll be able to cross that out. Okay, I'll go ahead and do that. So that's gone. And now, again, to solve for t, we'll just divide everything by that coefficient. Okay, so you'll find that when you're doing these in your homework, they all kind of, the process is the same for all of them. Alright, so that decimal will divide. We'll end up with t is equal to, and now I'm going to use my calculator for all this. If you can, try to make your calculation be the very last. Try to save doing any calculations in your calculator until the last step. That will ensure the most accuracy. So I'll say the natural log of, in parentheses I'll type 40 divided by 25.2. I'll close those parentheses, and then I'll divide that by that decimal. Now I'll hit enter. Alright, so this is my decimal approximation. So this is roughly to the nearest tenth of a year. This would be 21.1. 21.1 years. Okay, that's the time, roughly the time it would take to reach 40 million. And of course we know it takes about 32 years to reach 50.4 million. Alright. Well, a lot of these problems are going to be very similar to this one, guys, just different context. Let's look at another one, and then we'll do a part 2 video to finish up this section. What we have right now is, what you'll realize is that the growth rate and the doubling time are related, okay, right here. Okay, so if you're trying to find the doubling time, and you can use this formula right here. That's actually what you're doing when you solve an equation for t. Okay, you end up with the ln of 2, and what did we do with the ln of 2? We divided it by k, the growth rate, okay? And that's how we found t. So if you want to, you could just use this. It would save you some steps. Anytime you're trying to find the doubling time, you can use this formula right here and just plug in for k. Anytime you're trying to find the growth rate and you know t, a value for t, you can just use this formula right here. Okay, in other words, you would just be solving some exponential equation, but k would be your variable there. So you go through all the same steps. All right. My computer froze. Okay. All right, so interest compounded continuously. Let's see. Okay, well, it looks like my image froze again, but that's okay. All right, so if you recall, I was talking earlier about how in reality interest is not compounded continuously. It's compounded at specific points in time. Okay, so for example, once a month or once a day, or it can even be compounded like once a second, okay, or once a millisecond, okay, because lots of times big banks, they'll borrow from each other, but they may only borrow or hold that money for a very short period of time, and so they'll look at calculating or compounding interest over a very small fraction of time, an interval that's a very small fraction of time. Okay, but anyway, nonetheless, we're going to be using the same template right here. And let's look at example 2. It says, suppose that we invest $10,000 at an interest rate of 5.4% per year, compounded continuously. Okay. Now, if the word continuously was not in this, we would be using this formula up here. Okay, right here. If it was compounded quarterly or monthly, etc. When it's compounded continuously, this piece of the formula converges to this irrational number e. So that's why we're using this formula template. Alright, so part A, similar to the previous problem, it says find the exponential function that describes the amount in the account after t years. Okay, so again, I'm just going to plug in those parameters for part A. So P of t, or you could call this A of t if you want, because this is a financial problem, is equal to the initial value. Well, in this case, using that generic formula, it's the $10,000. times e to the power of k times t. Well, k is 5.4%, which is a decimal, will be 0.054. Oops. Do a little better job of writing that 4 and then times t. Okay, so this is my function right here, specific to this particular problem. Now, part B says, what is the balance after 1 year, 2 years, 5 years, 10 years? So all we're going to be doing for part B is just evaluating this function for those different values of t. Okay. So you can do all this in the calculator if you'd like. And let's see, 5.4, that's not a bad interest rate. Interestingly, at the time of this recording, I guess it was about, I'm trying to think, it was earlier, was it this year? I think it maybe was this year. Anyway, about a year ago, you could find some money market accounts that would pay you close to 5.4% interest, or APR. Okay. Now that has come down some. It has come down. Now I think it's about 4% because the Federal Reserve has lowered interest rates several times, 1/4 of a percentage point each time. But anyway, I'm digressing here. All right, well, all we're going to be doing for these problems, guys, is evaluating this function that we came up with for different values of t. Okay, the first one I'll write out explicitly. The rest of these I will not, because you can just use your calculator to evaluate these. Alright, so 10,000, and type it in exactly the way it's written. Okay, second the natural log key to get your e, and then up here we're going to have k 0.054 times, and we'll plug in these different values of t, times 1, we'll hit enter, and we'll round these to the nearest cent. Okay, so this will become $10,554.85. Okay, let me put a $sign there. And for the rest of these, I'm just going to use my calculator. And if you remember that trick that I showed you, you can say second and then hit the enter key for entry. You know, reproduce this, and you can come back and just replace your input value. So instead of 1, I'll use a 2 and hit enter. And now after 2 years, it's $11,140.48. Let's see, how much change? Oh, 48 cents, okay. Okay, so you can see it's grown in 2 years over $1,000 here. And I'll just repeat the same process. I'll say second, enter for entry, go back and replace that 2 with 5 years. Now we've got $13,099.64. Okay, so now it's grown over 5 years. It's increased by over $3,000. And then finally, for 10 years, hit enter. Oh, now we've got $17,160, and to the nearest cent, this would be 7 cents, 0.07. Okay. All right. All right, now part C says, what is the doubling time? Well, if you're looking at this sequence here, you can see that after 10 years, we're starting to get close to having the initial amount doubled. Okay, so it's going to have to be more than 10 years. For part C, the doubling time, well, we could do it the way we did the last one. We could say, well, to double this, that means 20,000, so you could set this function right here equal to 20,000 and solve it for t. Or you can use this formula right here. Okay, and it'll save you all those steps. So that's what I'm going to do. Okay, so I'll rewrite it over here so we'll have it to reference. Natural log of 2 divided by k. So if we want to find the doubling time, we'll take the natural log of 2 and divide it by k, which k in this case is 0.054. And that'll give us the doubling time. So you can see this saves us a lot of work, doesn't it, guys? This would be the same, you know, as if we did the last one. If we had taken this function set equal to 20,000, divide both sides by 10,000, then give us 2. Take the natural log of both sides, you'll end up with the natural log of 2, and ultimately have to divide by k. Alright, so I'm just going to plug this in. So the natural log of 2 divided by 0.054, the rate. And this makes sense. See, after 10 years, we've got about 17,000. So to the nearest tenth of a year, this would be about 12.8. So roughly 12.8 years, our investment will have doubled in value. Okay. All right. I've got 2 examples left. I think this is a good stopping point. We'll do the last 2 in the part 2 video.